Welcome everyone to this Haskell Symposium talk. I'm just going to start off today with a simple coding exercise. So I'll be defining a function, let's call it tuple, with the following type. So I wanted to have type for all A, for all B, and then a tuple of A and B. The implementation of this function should be fairly straightforward, as we'll just take two arguments and place them in a tuple. Like this. Now, later on in my program, I want to define a second function with a new name. Let's call it my tuple, but with the same behavior. So I'll just define it as a synonym for the existing function. So later on, when I use this function, for example, in the main, I want to do so as follows. So I want to call my tuple, and I'll pass in a first argument, let's say 5. And then I want to specify that the second argument needs to be a Boolean. And I'll do this using visible type applications as follows. I'll then just pass in a second argument, for example, true, so that I can print the outcome. Now you can already see that my editor is complaining about this. And in fact, when I load this program in GHCI, it'll give me a type error saying that I can't use type applications here. Though if I load the same program in GHC9, then it compiles just fine. So clearly, when going from GHC8 to GHC9, steps have already been taken to improve this behavior. Though it turns out that this behavior is still quite fragile and somewhat hard to predict. So for example, if I just do something silly like eta expanding this definition, which really shouldn't make a difference, and I reload the file, well, then suddenly it breaks again and we get the same type error we had before. So the question I'd like to answer today is, can we further improve upon this situation when going to GHC10? And in order to help me answer this question, let me just call my nearest tweak consultant.
Hello.
Hi, Richard. I have a question for you. So I have a couple of examples where both GHC8 and GHC9 show some somewhat fragile and hard to predict behavior. And I was wondering whether we could fix this when going to GHC10.
Well, these issues are very interesting, and it's quite a bit more subtle than you might think. So let's take, for example, the identity function. So we can have this id function, as we see here, of type for all A arrow A. But when we use that, it has to be made concrete. At some point, when we say, for example, id of true, we have to instantiate this polytype with, or this A with bool, giving us the type bool arrow bool. And so there's a lot of flexibility in how we design this feature. For example, if we have myid equals id, well, we might instantiate eagerly. I haven't passed any arguments to id here, but I could say that instead of having this polytype with for all A, I could instantiate this with a unification variable. So here I'm writing that as u1, and it's essentially a type variable that we don't know what it stands for yet. We can almost think of it as just sort of a hole in the type that as we continue to do type inference, we might fill in. In this case, type inference doesn't tell us anything more. We don't learn anything more about u1. So when we're inferring the type of myid, well, we're just going to take this unconstrained variable, generalize over it, and then get another polytype. The difference is in this new polytype, we see that there's these little braces around the A. That marks the A in the last polytype written here as an inferred variable. Right? We don't actually use inferred variables for visible type application because maybe there's many of them and we can't really predict the order that they occur in. So with eager instantiation, that's what I'm describing here, where as soon as we see id, we actually instantiate it to a unification variable right away. We're going to get this type at the bottom here for myid. On the other hand, we could have lazy instantiation. So in lazy instantiation, we see id, and then we don't instantiate. And so that means that we can actually infer a type for myid that still has the exact same type as id has, and that means that now myid can be a drop-in replacement in all scenarios for id. GHC has moved around in this space a little bit. So GHC 7 used eager instantiation. Then to accommodate visible type application, GHC 8 uses lazy instantiation. But we see here in the image that the GHC 8 icon isn't all the way over on the lazy side. And that's because some practical concerns still compel us to use eager instantiation in certain places. A key place where eager instantiation is still used is that right before we generalize the type, the inferred type of a definition, we instantiate it first. And this gives us a slightly more predictable type inference and slightly easier to understand type inferred types. But the fundamental action of the type checking algorithm in GHC 8 is lazy. In GHC 9, we went back to eager because that seemed like a simplification over this sort of mixed economy that we use in GHC 8. But it turns out that eager versus lazy isn't the only issue at hand. And your tup and my tup example, actually that's not really about eager and lazy. That's instead about deep versus shallow. So here we have our tup type up on the screen. And if I instantiate this tup type deeply, what that means is I take all quantified variables even after arrows and instantiate all of them. So in this case, that means that when I instantiate tup, I'm going to instantiate both A and B. GHC 8 does deep instantiation. GHC 9 does shallow instantiation. So we've already also flip-flopped on this. Here in tup, we see that when we do deep instantiation, then we affect both of the variables here. On the other hand, in this version, this is what GHC 9 does. This is shallow, which means that as soon as we see an arrow, we're going to stop instantiating. And so in this case, you see on the bottom here that we've only instantiated the first variable A. We have not instantiated B yet. So this is actually why we see the difference in behavior between GHC 8 and GHC 9 that you demonstrated at the beginning. That's because in GHC 8 we do deep instantiation, meaning that this B variable ended up being instantiated, then regeneralized in the type of my tup, so it meant we couldn't use it with visible type application. GHC 9 only instantiates the A, meaning that this B variable is still around in my tup. In this diagram, we see now not only do we have eager and lazy going left to right, but we have deep and shallow going bottom to top. So GHC 7 was both deep and eager. There's ways that we can observe deep in GHC 7, although eager is harder to observe because we don't have visible type application there. GHC 8, as I explained before, is both lazy and a little bit eager in some situations, but it's always deep. GHC 9 is always eager, but now it's shallow. And so a big question is, what's best? Do we want to use which spot in this or which quadrant in this axis set of axes do we want to use? And we seem to be having a hard time figuring it out. All of these are sound, but what's best for users? Makes me wonder, should we organize a user study? What do you think?
Thanks for that interesting discussion. So, while I would like to do a big user study, I'm a bit worried that organizing a big user study with 4 different versions of GHC would get quite expensive and quite hard to organize fast. So I'm wondering, could we try to approximate this result using a more formal method? And that's the second question that we're trying to answer today. How can we approximate evaluating a user-facing design decision, but using a more formal method of evaluation? And we're going to be tackling this using the concept of stability. So with this we mean that making small innocuous changes or program transformations to the code should not have a major impact on the meaning of the code. And we're going to start doing this by constructing a small list of program transformations or properties that we want our compiler to satisfy. And the first one of these properties is, for example, that let inlining should be type preserving. So, for example, if we have a function or a value bar that uses another definition foo, well then inlining the second definition should not alter the type of bar. And the reverse should hold as well. Extracting some implementation from bar into a second definition should not alter the type of bar. Furthermore, let inlining and let extraction should not influence the runtime outcome of this function. So with that I mean that if we evaluate bar, then the outcome or the value should remain the same in both cases. Looking at another example, if we duplicate an equation in a function definition, while being a bit silly, this should never alter the type of this function. And let's have a look at one more property. Eta expanding a function definition, like foo in this case, which has a function type, well then that should not change the type of foo either. Now we've enumerated all these properties in this table, and the next step is to evaluate our different forms of type instantiation against these 5 properties. And we're going to do so as follows. So the first step is to formalize our type system family. And with that we mean that we're going to formalize our type system, but parameterized over the form of type instantiation. So if later on we instantiate our type system family with a specific form of instantiation, well then we should get one of the 4 type systems as we discussed earlier. Next up, we need to formalize the different transformations or properties that we expect our compiler to satisfy. Some of these we've seen before, but the paper introduces a number of additional properties as well. And then finally, we need to evaluate all of our different properties against our type system family. Now you can find the full proofs along with a set of counterexamples in the paper, but the outcome looks as follows. So we conclude that our recommendation for GHC 10 is lazy shallow instantiation. It preserves most, though not all of our different properties, but this makes it the most stable form of type instantiation. Again, you can find the full discussion along with additional properties and a full set of counterexamples in the paper. And this neatly brings us to the title of this talk. We hope you enjoyed the talk and will be available afterwards for any questions or further discussion on this topic.